Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. Welcome to episode 5. In this episode, we will talk about resistors and voltage drop. Both, resistors and voltage drop, are necessary prerequisites for understanding electric circuits. We will not go into details about various types of resistors, and their manufacturing process, but rather, we will devote our attention and time to explain the nature and the role resistors play in circuits. We will shortly touch on the subject of resistors in parallel and serial in electric circuits. Next, we will explain what is voltage drop and why is it important to understand its concept and role in electric circuits. So, let's begin. The resistor is a passive element in electric circuit, whose role is to regulate and limit the flow of electric current. First, let's tackle what does it mean that resistor is passive element. An element that does not produce or supply power in electric circuit is called passive element. Passive element can receive electrical current, and after that, it can absorb it, or dissipate it in form of heat, light and etc. Opposite to passive elements, an active element is that one which supplies electric circuit with power. Typical representative of an active element in circuit is power source, for example, a battery. Now, let's see how resistors play the role of regulating the flow of current in circuits. Let's draw up a simple circuit, consisting of power source and load. The term load in electric circuit is just another fancy name for any component in electric circuit that consumes electric power. For power source in our circuit, we will use 5 volts battery, and for the load, we will use a simple LED diode. When we flip the switch and close the circuit, the current starts to flow, from positive end of battery, through LED diode, and back to negative end of battery. Since there is nothing to limit the flow of the current in the circuit, our battery will give all what it has, to power up and keep the circuit supplied with energy. In simple terms, it will give its maximum. On the other hand, our LED diode is manufactured in such a way, that it can withstand a maximum of 20 milliamperes of continuous current. By itself, a LED diode cannot regulate how much current it will receive. It is not made to do so. So, our diligent battery will start to supply our circuit. In the beginning, all of the power in the circuit is being absorbed by the LED diode, so our battery attempts to supply more and more. This manifests itself by current in the circuit rising from 0 amperes to 0.001, then 0.01, and so on. This rise of current in the circuit continues, and that supplied current is being absorbed by our LED diode, which starts slowly to glow with more and more luminosity, until the current supplied from our battery reaches 20 milliamperes. At this point in time, our LED diode reaches the maximum of current it can absorb, and it glows with maximum luminosity. But our battery keeps producing and pumping more and more current into the circuit. On the other hand, our LED diode now starts to struggle with more and more current. The function of LED diode is to transform electric current into light. As current in electric circuit is now more than 20 milliamperes and continues to rise, our LED diode is having more and more hard time to convert all of that current into light. You can visualize this problem as an analog to a water being poured in a bottle through the funnel. When we fill the bottle to the top, but continue to pour water into the funnel, the water will start to spill over both from the bottle and the funnel. But our LED diode is not designed to just start spilling current around itself. By design, the materials from which LED diode is made, will start to heat up. Since LED diode cannot manage to convert all the supplied current into light, the rest of the excess of the current is now being transformed into heat. Eventually, as the supply of the current from battery continue to rise, LED diode is unable to transform all of the supplied energy both into light, and now into heat as well. When LED diode reaches its maximum ability to transform the supplied power to light and heat, it burns out, because the excess heat that is being generated inside LED diode, cannot be dissipated quickly enough into surrounding air, so our LED diode melts itself from the inside out. At that point in time, the circuit is broken and value of current in the circuit is 0. This all happens very quickly, in the blink of an eye. As we previously mentioned, the function of the resistor in electric circuit is to regulate and limit the flow of the current. Resistors do that by converting excess of the current into heat, which then they dissipate into surrounding air. The resistors have two main features: their resistance, measured in ohms, and their rated power dissipation, measured in watts. The resistance of resistor ranges from 1 ohm to even a couple of millions of ohms. Bigger the resistance of resistor, less current will flow through the circuit, and vice versa. To be precise, the amount of current flowing through electric circuit is inversely proportional to value of the resistor in the circuit. We use capital letter R to note the resistors in circuits, and value of resistance is measured in ohms, and noted with Greek letter omega in square brackets. As for the second feature of the resistor, rated power of dissipation, it simply says how much of current the resistor can transform into heat, and dissipate that heat in surrounding air. This feature is noted with capital letter P, and as previously mentioned, measured in watts, and noted with capital letter W, in square brackets. But more about this, at the end of the video. Let's get back to our schematic, and this time, we will put the resistor between battery and LED diode. As previously shown, the problem with original circuit, one without resistor, was that flow of current in circuit was unregulated, and as a result, our LED diode burned out. To mitigate this problem, we introduce a resistor in circuit. As we have said, the purpose of resistor is to regulate intensity of the electric current in the circuit. Now, the most obvious question is, how big a resistor do we need? Well, that depends on two important factors. First one is, how much current we want to allow in our circuit. Do we want 1 ampere, more, or less? How do we determine this? Usually, the amount of current we want flowing in the circuit is dictated by something called a load. Load is a component, or a device, that consumes power provided by circuit's power source, and performs a work. In our example, a load is LED light, that consumes power from a battery, and work it performs is illumination. But we still do not know how much current we need to allow in our circuit, or how big of a resistor do we need. How to find out answer to all of this? Answer to this question lies in something called LED specifications. The specifications are provided by LED manufacturer. It is a document that contains information about all important characteristics of a LED diode, from its dimension, through electrical properties, to the mounting parameters. Usually, specifications are provided either by manufacturer, seller, or they can be simply looked up on the internet. The table on the screen lists some of most common electrical characteristics of a LED diode. Now, let's go over them, one by one, and explain what is the meaning of each one, and how do they impact our circuit. First, and the most important parameter for us is, continuous forward current. This parameter tells us what is the amount of current that is safe to run through a LED diode. Simply put, the LED diode will perform its job when we let 20 milliamperes of current through it. Now, the most obvious question that pops up is, can you go higher or lower than 20 milliamperes? You can surely go lower, but that will dim the brightness intensity of our LED diode. At lower current, it will not shine as bright as it should. Now, can we go higher, and how much higher? The second parameter answers that question. Peak forward current parameter tells us, what is the maximum value of current, that is safe to let run through our LED diode, but only, and we repeat, only for a very short period of time. That short amount of time is measured in milliseconds. If you let the diode run for a longer period of time, with this much of a current flowing through it, you will burn out your diode. Next parameter is forward voltage. It tells us what is potential difference that develops between terminals of LED diode when current is set at 20 milliamperes. We have previously learned that potential difference is called voltage. So simply put, when we let 20 milliamperes run through the LED diode, there will be 2.9 volts of voltage drop across the diode. More simply put, this tells us that we need, at least, power source that is 2.9 volts or bigger as our power source. If we have 1.5 volts power source, our LED diode will not work. The reverse current parameter tells us how much of current will flow through the diode when we switch position of terminals, or simply put, when we put the diode upside down. And last, but not least, the power dissipation parameter tells us the maximum value of power in the form of heat that LED generates, that can be dissipated in the surrounding air. Now, since we have familiarized ourselves with LED parameters, let's get back to our circuit and plug in some numbers. We are back. So, let's plug in some numbers. From LED specifications we have learned that the optimal current for LED circuit is 20 milliamperes. So that is first parameter set. Now, for our power source, we know that we need, at least, 2.9 volts, or higher, but batteries, or other types of power sources usually don't come in that value. If you have watched our pilot season, book on DS0138 oscilloscope, you saw how we have, by using circular economy and sustainability framework, repurposed old computer power supply unit to become power source for our projects. For this example, we will choose 5 volts output from PSU as our power source. Now, we have our power source set, and we have determined the current we want to run through our circuit. So, how do we calculate the value of resistor? From LED specifications, we have learned that when 20 milliamperes of current runs through circuit, there is 2.9 volts of potential difference that develops between LED terminals. On one hand, we have 5 volts power source, and on the other hand, we have 2.9 volts of voltage drop across LED terminals. So, the only place where difference of 2.1 volts between power source and LED voltage drop can go is between terminals of our resistor. So, we say, when there is 20 milliamperes of current running through our circuit, in this particular design, there will be 2.1 volts of potential difference between resistors terminals. That potential difference is called voltage drop across the resistor. Using Ohm's law, let's calculate resistance of the resistor. Ohm's law defines relationship between current, voltage and resistance in the circuit. It can be expressed in 3 ways. The first way says that voltage is directly proportional to the product of current and resistance in the circuit. The second way of expressing Ohm's law says that resistance is directly proportional to voltage, and inversely proportional to the current. And the third way of expressing Ohm's law says that current is directly proportional to voltage and inversely proportional to the resistance. Now, using second expression of Ohm's law, we can calculate that resistance of resistor required for our circuit is 105 ohms. Now, calculating the resistance of the resistor is just a first factor in our choice of the resistor. Remember just from a couple of minutes ago, we said that, when we choose the value for the resistor, there are 2 factors to take into consideration. The first one is value of resistance of the resistor. The second one is rated power dissipation of the resistor. Choosing the right resistor with appropriate value for rated power dissipation is most important decision when designing and building electric circuits. We will deal with that at the end of this video, but for now let's get back to our circuit and give our final remarks. When determining and calculating the value of resistor for our circuit, the first guiding principle was the desired current we wanted to run through our circuit. We obtained that value from LED specifications. After that, we needed to choose appropriate power source. Power source must generate voltage that is at least equal or preferably higher than one that develops as potential difference across terminals of LED diode. That potential difference is denoted in LED specifications as forward voltage, and in general, in electric circuits is referred to as voltage drop. After that, by using Ohm's law, we calculated the required resistance for our resistor. Now, this is an ideal situation. In this scenario, ideal means that the power source provides constant 5 volts of power output. Also, it implies that the value of resistor remains constant through time, regardless of changes in circuit and ambience temperature, and also implies that all of the LED's characteristics remains at constant value as long as the circuit is powered. However, as we have previously said, in real life, there is no ideal scenario, especially when it comes to electric circuits. In real life, in electric circuits, there are always some fluctuations in circuit parameters, whether being caused by changes in voltage from power supply, that as a result causes changes in current flowing through the circuit, or there is an excessive heat generation from components, that as a result impacts the performance of components, changing their electrical characteristics. For example, a change in power output from power source will cause change in amount of current flowing through the circuit. That will, as a result, impact voltage drop characteristics, both in resistor and LED diode. And at the end, not every component is an identical clone, even if they have exact same electrical characteristics. For example, two resistors from same batch, with identical nominal value of resistance, can have different resistance when measured by multimeter. That difference from nominal and measured value is called tolerance and is expressed in percentages. Furthermore, when you calculate the value for resistor's resistance, you can get any value. But, as a fact of life, the resistors do not come in all possible values. Resistors are being manufactured with some typical values, for example 1, 10, 50, 100, 1000 ohms, and so on. So, what happens when we do not have a resistor of required value? Well, we compromise. We do next best thing, and that is, we choose a resistor with next higher value that exists. In our case, since there isn't 105 ohm resistor, the next best thing available to us is 150 ohm resistor. Now, there is a legitimate question: why don't we choose 100 ohm resistor? Why go that much higher with 150 ohm resistor, when there is resistor available with almost exact value that we need, a 100 ohm resistor? Well, as far as resistors are concerned, there is a rule of thumb that says, when there is no resistor of required value, go with next available higher value. And here is why you should always adhere to this rule. Consider scenario where you disregard this rule of thumb, and you go with resistor of lower value than required. Let's say, that by some bad misfortune, there is a sudden increase of voltage in power source. As a result, there is an immediate increase in current flowing through the circuit. Since you have opted for a lower than required resistor, now there is substantial increase in amount of current going through the circuit, and as a result, our LED diode is generating more and more heat, in attempt to dissipate excessive current it is receiving. For a short period of time, this will not cause problems, but if we leave our LED to run for hours and days, that excess amount of heat that LED generates due to increase of current in circuit, will in time damage the LED diode, causing it to lose brightness, and at the end, it will burn out. On the other hand, had you followed the rule of thumb, the higher value resistor would have no problem in regulating the excess of current, and it would have protected our LED diode from overheating and burning out in the end. The video playing in the background during this narration is our prototype of circuit schematic used in this video. Now, let's tackle the voltage drop. A quick recap of current and difference in potentials is in order before we proceed. As we have mentioned in our previous videos, if we have two points with different potentials, let's name them A and B, and let's assume that point A is electrically charged more in comparison to point B, or simply put, point A has a higher potential than point B. The difference in those two potentials is called voltage. If we establish route from point A to point B, by placing a conductor, then the current will start to flow, in direction from point A to point B, until both points are at same potential. In that point in time, the difference of potentials between point A and point B will be zero, thus there is no voltage, thus there is no more current. The most important thing to remember from this is that in order for the current to exist and flow, there has to be a difference in potentials. Now, since we have that sorted out, let's get back to our LED diode, and drawing back on from what we have previously learned, let's put one blue LED diode on our screen. For now, we will set aside current requirements, as we will be dealing with voltage drop. We know that in order for diode to glow, there has to be a power source of at least 2.9 volts. Let's mark ends of diode's terminals as P0 and P1. In order for our LED diode to glow, the potential difference between point P1 and P0 has to be at least 2.9 volts, assuming appropriate current of 20 mA is available in the circuit. Now, let's introduce a green LED diode. Since green and blue LED diode will now share a connection point that is already marked P1, we will just add P2 mark at the top terminal of green LED diode. Same as with a blue diode, for green LED diode to glow, the potential difference between its terminals has to be 2.9 volts or higher. At last, let's introduce red LED diode. Now, the green and red LED diode will share connection point already marked P2, and we will add P3 mark for top terminal of red LED diode. As same as before, in order for red LED diode to glow, the potential difference between its terminals has to be 2.9 volts or higher. Now, let's reference point P0 as our 0 volts reference point. That immediately implies that point P1 will be at 2.9 volts difference in potentials, regarding point P0, same goes for point 2 and point 3. The difference in potentials between each two subsequent points will be 2.9 volts. As a result, the point P3 will be at 8.7 volts of difference in potentials, in respect to point P0. Can you guess what will happen if we connect these three LED diodes on out 5 volts power supply? If you have guessed nothing, you would be right. Now, let's analyze why our LED diodes did not lit up. Each electrical component, by its design and manufacturing process, has some internal resistivity. That internal resistivity can be pure resistive, capacitive, inductive, or combination of some of them, or combination of all of them. So, in order for current to flow through our hypothetical electrical component, there has to be some external force that will push current through the component. The measure of resistance that such external force has to overcome, in order to push the current through the component is called voltage drop. In our experiment we used LED diode. From electrical specifications document we know that LED diode requires at least 2.9 volts of something called forward voltage in order to glow. So, to put things into perspective, our LED diode has some internal resistance, and in order for current to flow through it, the power source has to put out voltage that is equal or higher than 2.9 volts. In general, every electrical component in electric circuit introduces some internal resistivity to the flow of current. In order to overcome that resistance, the power source must produce force in form of voltage, in order to overcome that resistance, and provide the flow of current in electric circuit. Simply put, the voltage drop pushes back against power source, by introducing difference in potentials at its terminals. If such introduced difference in potentials is larger than supplied voltage from power source, there will be no current in the circuit. Consequently, if such difference in potentials, introduced in circuit by the component, is smaller than voltage from power source, the current will flow through the component and the circuit. Let's get back to our LED setup and put things into perspective. We have defined voltage drop as difference in potentials that is introduced at terminals of each LED diode, which is a result of LED's internal resistance. So, each one of our 3 LED diodes pushes back against power source with force that is equal to 2.9 volts. Combined resistive force of all of 3 LED diodes is 8.7 volts. So, in order for power source to successfully pushes current through the circuit, the power source has to have voltage of 8.7 volts, or more, in order to do so. As with resistors, since we do not have 8.7 volts power source, we will use a rule of thumb, and select next best available voltage for power source. In our case, the next best thing is 12 volts rail from our repurposed computer's power supply unit. Let's now do a proper setup. Having in mind changes in parameters, let's recalculate the value for our resistor. Since now we have a new power source of 12 volts, 3 LED diodes with combined voltage drop of 8.7 volts, plugging the numbers into equation gives us value of 165 ohms for our resistor. You may have noticed that our multimeters do not show exact numbers from our math. This is a part where real life comes into play. All this theory about LED diodes, voltage drops and power sources, refers to an ideal components. As previously said many times, in real life nothing is ideal, especially when it comes to electronic components and circuits. Each and every component, starting from power source, through breadboard, DuPont wires, and LED diodes will introduce known, or unknown voltage drop, thus certain discrepancies and errors will creep in, resulting in values that are a bit off from our math. Well, that's a real life for you. This would not be a complete tutorial on resistors and voltage drop, if we do not touch on 2 more important subjects regarding resistors. First, let's deal with resistors in series and in parallel. As we previously saw, sometimes when we do a math to calculate the value of resistor for our circuit, we may come with some odd value that no physical resistor match. So, let's first see what happens when we place 2 resistors in series. Placing 2 resistors in series means, we concatenate 2 resistors, by attaching one terminal from first resistor, to one terminal from another resistor. In this arrangement, both resistors share same current flowing through them. But, what about voltage? From previous part of video, we know that each component introduces voltage drop in circuit. Voltage drop is measure of internal component's resistivity, that component exerts against power source. Now, there are 2 scenarios. First one is, where resistors have different values. Let's do some math. Let's assume power source of 5 volts, and let's choose 2 resistors, one with 1000 ohms, and second one, 10,000 ohms resistance. How do we determine current running in the circuit, and what are the respective voltage drops over first and second resistor? When we have 2 adjacent resistors in circuit, that are in series, their combined resistance is sum of each individual resistance. So, we can redraw our circuit in manner, that now, instead of 2 different resistors, we replace them with a single resistor, that has resistance that is summed resistance of both resistors. Using Ohm's law, we can calculate current flowing through circuit as voltage divided by resistance. So, in our case, we divide 5 volts with 11,000 ohms, and we get 0.00045 amperes, or 0.45 milliamperes. Since, now we know the value of current running through circuit, it is an easy math to calculate voltage drop over each resistor, since the value of each resistor is known constant in the equation. Now, we can go back to our original drawing of circuit and do the math. So, for our first resistor, we multiply its value of 10,000 ohms with the current, and we get voltage drop of 4.55 volts. Same with the second resistor, we plug in the numbers of 1000 ohms for resistance, and current, and we get 0.45 volts of voltage drop across second resistor. Now, sum of voltage drops across each component in the circuit must be the same as voltage value of power source. If that is not the case, then our math is wrong. Now, for the second scenario, let's quickly see what happens when we have two resistors in series with identical values. Let's redraw our circuit, and let's have both resistors marked as R1 and R2, and let's assign them both 10,000 ohms resistivity. Drawing on previous knowledge, now combined resistance of both resistors will be 2R, or 20,000 ohms. Current running through the circuit is now 5 volts divided by 20,000 ohms, which gives us 0.00025 amperes or 0.25 milliamperes of current. Plugging numbers back to Ohm's equation for calculating voltage, the result gives us the same voltage drop across both resistors, 2.5 volts. Since in this arrangement, when we have two identical resistors in series, voltage drop across each one of them is the same, we call this arrangement of resistors, voltage divider. So, in conclusion, if you do not have a resistor of required value, you can always connect several resistors in series, to get exact or close enough value of required resistivity. If all of the resistors in series are the same, then voltage drop across each and every one of them is source voltage divided by number of resistors in series. Now, we do the same for resistors in parallel. Placing two resistors in parallel means that now, both terminals of the resistors are connected to the same point. Now, in this arrangement, both resistors share the same voltage, but the current flowing through each resistor is different. In this kind of circuit, now there are two different currents running through two different parts of the circuit. We will mark current running through resistor R1 as I1, and current running through resistor R2 as I2. As before, let's assign resistor R1 10,000 ohms resistivity, and to the resistor R2 1000 ohms resistivity. Now, there is no point in calculating voltage drop across each resistor, as both resistors are directly connected to power source, and there is no voltage drop over any of them. But there is a matter of finding out values of current running through each resistor. As was the case with resistors in series, here, we will also draw an equivalent circuit, replacing resistors R1 and R2 with equivalent resistor R. Now, the value of equivalent resistor is given by formula, inverse value of equivalent resistors is equal to sum of inverse values of each individual resistor. So, let's plug in the numbers. We know values for R1 and R2, so equivalent resistor has inverse value of 1 over 10,000 ohms, plus 1 over 1000 ohms, which gives us the value of equivalent resistor of approximately 909 ohms. Now that we know value of equivalent resistor, calculating current is matter of plugging the numbers into Ohm's law for calculating current. The equation gives us value of 0.0055 amperes, or 5.5 milliamperes. Now, let's get back to our original circuit, and calculate values for currents running through each resistor. Since we have been given values for voltage and resistivity of each resistor, finding values for currents is matter of plugging the numbers into Ohm's law equation for calculating current. So, for resistor R1, we have that current I1 is directly proportional to voltage, and inversely proportional to resistance. That gives us value for I1 of 0.0005 amperes, or 0.5 milliamperes. Plugging numbers for I2 gives us value for current of 0.005 amperes, or 5 milliamperes. Now, sum of all individual currents running through each resistor must be equal to current calculated running through equivalent resistor. If that is not the case, then our math is wrong. Now, let's see what happens when we have two resistors with identical value in parallel. Let's assign both resistors 10,000 ohms resistivity. Drawing on previous knowledge, now the combined resistivity of both resistors will be 5,000 ohms. The current now running through the circuit is 5 volts divided by 50/100 ohms, which gives us current of 0.001 ampere or 1 milliampere. Calculating current running through each individual resistor is matter of plugging the numbers into appropriate equation of Ohm's law for calculating current. We can see that equations gives us the same value of current for each individual resistor in parallel. So, we can conclude that in this arrangement, when we have two identical resistors in parallel, they act as current dividers in electric circuit. So, in conclusion, if you do not have a resistor of required value, you can always connect several resistors in parallel, to get exact or close enough value of required resistivity. If all of the resistors in parallel are the same, then current running through each and every one of them is the same, and that value is circuit current divided by number of resistors in parallel. The table on the screen gives us a summary of previous presentation about resistors in series and resistors in parallel. Now, somewhere in the beginning of this presentation, we have mentioned that resistors have two important defining characteristics. First being their resistivity, measured in ohms, and the second one being their rated power, measured in watts. Now, let's give a quick overview of resistors' rated power parameter, and see how resistors in series or in parallel can help us in situations where rated power is not adequate for our circuit design. Now, the last thing on our list, regarding resistors, is explaining resistors' power rating parameter. Before we dive into this, let's define, in general, what is power. By definition, power is rate of energy, consumed, or produced, in a unit of time. DC power is calculated as product of voltage and current. In equations, it is marked with capital letter P, and it's measured in watts, denoted with capital letter W, in square brackets. Now, here on this channel, we are more interested in truly understanding something, rather than just spewing out some old dry definition, so, let's see, what is all this fuss about the power? Nothing better, on how to explain complex concepts, than to draw from real-life examples. Now, we all have smartphones or tablets, and chance is, that you are using one to watch this video right now. All these fancy little gadgets come with chargers. One of the main characteristics of chargers, is how fast they can charge our phone or tablet. You have probably run into ad, or read the specification, that your charger can fast charge your phone with 15 watts, or 45 watts, or even 60 watts of power. The more power our charger can deliver, the faster our battery will charge. Our common smartphone USB charger operates at 5 volts. So, if our charger charges smartphone with 15 watts of power, that means there is 3 amperes of current running from charger, and charging out battery. Next most common place, where we come in contact with term power, is our electric bill. No matter where you live, there is something called power meter installed in your house, that measures your rate of power consumption. Usually, your electric bill will state that your consumption was 200 or 300 kilowatts-hour on monthly basis. Now, there is that unit of time, from the beginning of the definition. Simply put, if you multiply your power consumption, with any unit of time, seconds, minutes, or hours, you will get rate of power consumption in that unit of time. There is where that kilowatts-hour term comes from. So, if it takes 1 hour to completely charge our phone from 0 to 100%, and our charger delivers 15 watts of power, that means that one charging of our smartphone, consumed 15 watts-hour of power. If our water heater consumes 2 kilowatts of power to heat up the water, and we let it run for 1 hour, then we say that our water heater consumed 2 kilowatts-hour of power, being switched on for exactly 1 hour. Now, let's get back to our resistor. Clearly, our resistor doesn't charge our smartphone, nor does it heat up the water, so where does power come in play in this situation? Let's remind ourselves that role of resistor in electric circuit is to regulate and limit the amount of current running through the circuit. It does so by taking the excess of current, transforms it into heat, which it then dissipates in surrounding air. How much of current, at given voltage, can resistor dissipate as heat in the air, is by definition, resistor's rated power. For most of the resistors, their rated power is 1/8 of watt, or 1/4 of watt, meaning they can dissipate 125 milliwatts, or 250 milliwatts of power, respectively. Let's quickly draw up a simple circuit, consisting of 5-volt battery, and 10,000 ohms resistor. By using Ohm's law, we can calculate current in circuit. The equation gives us 0.5 milliamperes of current. Now, from definition for DC power, we know that power is product of voltage and current. This equation gives us power of 0.0025 watts, or 2.5 milliwatts. So, how do we read in all of this? In this circuit, the power source produces 2.5 milliwatts of power, or our resistor dissipates 2.5 milliwatts of power, in form of heat, in surrounding air. Since our resistor is rated at 250 milliwatts power of heat dissipation, it will have no problem regulating current in the circuit, and it will not heat up at all. All of the heat generated in the resistor will be dissipated in the air, and our resistor will remain to operate at ambient temperature. Now, let's see what happens when we change the parameters of our electric circuit. Let's assume that our circuit design requires power source of 24 volts, and that for some odd reason, we only have a bunch of 1000 ohms resistors available. As same as before, if we plug in the numbers, these parameters for voltage and resistivity, give us 0.024 amperes or 24 milliamperes of current running through circuit. Calculating power for resistor, we get that our resistor has to deal with 0.576 watts, or 576 milliwatts of power to dissipate as heat in the air. But our resistor is rated for only 250 milliwatts, so what happens now? At the beginning our resistor will brave out and do its best to dissipate all generated heat in surrounding air. But, as time progresses, the resistor will start to have a great deal of difficulties to dissipate all generated heat, and it will start to heat up itself. As time continue to progress, due to its own heat and incoming current from power supply, the resistor will lose all its ability to dissipate heat in surrounding air. At this point in time, the resistor will be super hot and it will start to smoke. Fairly soon, our resistor will burn out and cause break in circuit. So, what can we conclude from this example? If we have resistor with inadequate power rating, sooner rather than later, the resistor will burn out, due to excessive amount of heat, that resistor will not be able to dissipate. When designing and implementing circuit design, choice of adequate resistors, with adequate power dissipation rating is one of the most important parameters to take into consideration. Now, let's see if and how we can mitigate this problem. Obvious solution to this problem would be to procure a resistor with adequate power rating. But there is a catch to that solution. Resistors with higher power rating are usually bulkier and more expensive. If our circuit design asks for number of different valued resistors, then bill of materials can quickly add up to a significant amount of money. Next alternative would be providing some sort of passive or active cooling, in a form of radiator and fan. Again, this adds to bulkiness and increase in cost. Previously, we have learned that combining resistors in series or in parallel, as a result, can give us equivalent resistor, whose value can be easily calculated. So, if our design asks for 5000 ohms resistor, and all we have is bunch of 1000 ohms resistor, we can easily put 5 of 1000 ohms resistors in series, and get required value of 5000 ohms. Analog to that, if we have bunch of 10,000 ohms resistors, we can put two 10,000 ohms resistors in parallel, and get required value of 5,000 ohms. Also, combination of resistors in series and in parallel, can give us almost any value we desire. Combining resistors in this manner, provides us with an unexpected bonus. Placing resistors in series, or in parallel, or in combination, sums their respective power ratings. So, if we put two resistors, with power rating of 250 milliwatts either in series, or in parallel, equivalent resistor will now have their combined power rating of 500 milliwatts, respectively. By combining even more resistors, you can ramp up equivalent resistors' power rating up to several watts or even more. This concludes our video about resistors and voltage drop. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.